Yeah, all right. Because at the end of last class, probably most of you, couldn't focus on this slide. So let me just still repeat this slide quickly. Basis of solutions and Wronskian for that linear system version. Yeah, and this time n-dimensional linear system version. Yeah. So we did 2x2 version before, so now we generalize it to n by n version. All right. Yeah. All right. So our general equation, homogeneous y prime equals a y. Yeah. So here notation. First we need to solve eigenvalue problem. Yeah. So the typical eigenvalue problem, ax equals lambda x. Yeah. And we assume we have the solution. Yeah. So here we get the solutions. Yeah. The solution, two parts. One part eigenvalue part, lambda. There are k lambda, lambda values. Could be different, could be the same. Yeah. Yeah. Not necessarily different lambda values. Yeah. Therefore, each lambda value, there is a corresponding eigenvector. Yeah. We know how to solve it. Yeah. In last class, we did it for 2x2. Yeah, very simple. Yeah. For n by n, a little harder, but it can be solved. Yeah, not very hard. Yeah. All right. The corresponding solutions, here we are talking about y solutions, a vector solutions, a vector of functions that satisfy this equation. Yeah, that's the solution. The solution y vector sup k just equal to each eigenvector multiply the e function with the corresponding lambda kt as its exponent. That kind of relationship solution. Yeah. Yeah, because you can easily verify if you plug in to the original equation, you use the eigenvalue eigenvector equation, you can easily see this y vector satisfy the original equation. Yeah. So it is a solution. Yeah. But we have n of them. Yeah. 1, 2, 3. We have n of y functions. Now we want to see if these n y solutions form a basis or not. Yeah. Remember our key assumption. Yeah. In order to make our the whole situation easier, we make this assumption. Yeah. If we do not use this assumption, then the discussion could be very complicated. Yeah. All right, so what's that assumption? A has a linearly independent set of n eigenvectors. These n eigenvectors, we assume they must be linearly independent. Yeah. All right. This assumption here, if I use a simple diagram to explain our situation here, suppose that's all the possible cases. All right? Yeah. Yeah. So that assumption covers, this much case. All right? Yeah. But still, there is a portion it cannot cover. Okay? Yeah. Yeah. That part relatively harder. Yeah. So we do not consider that part for this class. Yeah. All right. So that's our assumption. Linearly independent. Yeah. Fundamental matrix. Yeah. We used this definition before about these n solutions. We put these n solutions together in a matrix, n by n matrix. Pack them in their natural order, n by n matrix. That matrix we call a fundamental matrix. So why fundamental matrix? Because we can represent the general solution from this fundamental matrix easily. All right. Matrix of eigenvectors. Similarly, we pack those n eigenvectors in a n by n matrix in this way. Same order, okay? Same order. All right. So now, based on the assumption, we know these n vectors, they are linearly independent. Then, what can we say about this X matrix? A matrix contains n linearly independent vectors. So what can we say about the whole matrix? So here we review linear algebra. Great. Invertible. So we practice that invertible. Invertible property is very important because we can take inverse. So we like invertible. So determinant not equal to 0. So that's another way to say invertible. If X is invertible, then it's determinant non-zero. The other side, the other way around, if the determinant non-zero, then it's invertible. So we can, just treat them. These two conditions are equivalent. All right. Now relationship between X and Y. Close relationship. So we want to see, can we find equation connected these two matrices? So Y, we can write it explicitly, containing X vectors, at the same time a set of functions using their corresponding eigenvalues. But this structure is a simple structure if we use the matrix product to look at that structure. All right. Here, another important thing we want to see if these n vectors are linearly independent. It is important. If they are linearly independent, then we can say they form a basis. They form a basis of the solutions. Otherwise, so we cannot say they form a basis of solutions. So we want to see this is true or not. All right. Now, so Y expression, that one, we can write it as a matrix multiplication product of two matrices. If you use the matrix product definition, you can see it. Because, so here, each row you multiply column, right? When you multiply column, this entry you multiply, all the first entries. First entries of all the columns. That's that one. Okay. Second one, multiply second entries of all rows. So that's the second column vector and so on. Okay. So this is a diagonal matrix. Diagonal. Okay. Diagonal matrix. So we use a capital lambda to represent this diagonal matrix. Because we use all their corresponding eigenvalues, lambda, little lambda. So here, capital lambda represent this lambda matrix. Okay? Then we can write capital Y equals capital X times capital lambda. Then, to see if Y matrix is invertible or not. Because this question, if these m vectors are linearly independent, that's the same thing we look at if Y matrix is invertible or not. Same thing. Yeah. So let's look at a Y matrix invertible or not. That's just like the same thing to look at determinant of Y not equal to 0 or not. Okay? So let's calculate determinant of Y. Here, we use a simple formula in determinant. Determinant of product of two matrices. Yeah, here. It should be two square matrices AB. Yeah, so last time I mentioned this. Because there is a possibility A is a rectangular matrix, B another rectangular matrix. Yeah, so that's a possible, oh, yeah, one student tried to get in. Yeah, all right. All right. Rectangular matrix way, then we don't have this formula, okay? A matrix is like this. B matrix is like that, okay? Yeah. So you may have a rectangular. So that's a possible case. A matrix, B matrix, yeah, product A and B, you know, this won't true. Yeah. Because A is a non-square matrix, B non-square matrix, their determinant not defined. No definition for non-square matrix for determinant. Yeah. Not defined. Yeah. So here, we need to check. Both matrices must be square matrices. Then we can apply this formula. Here, we have no such problem. All our matrices here, Y, X, capital lambda, all square matrices. Yeah, so we can apply that formula. All right, there, Wronskian, yeah, because for linear system, the Wronskian is defined as the determinant of the fundamental matrix. So that's the reason we bring the Wronskian concept here. Yeah. Because based on the Wronskian definition, for this linear system, homogeneous linear system, equals determinant of Y. Now we apply this property formula. All right, equals determinant of Y equals X times lambda. Okay, let's split the product of two determinants. Yeah, determinant of lambda easy to calculate, right? Diagonal matrix. Determinant, you just multiply all the diagonal entries. That's the determinant of diagonal entry, the diagonal matrix. Yeah. Simple. Another E function. Yeah. Adding up all the eigenvectors multiply T. Yeah. Yeah. All right. So that's X. We already know determinant of X non-zero. E function cannot be zero, right? Yeah. E function can never be zero. So non-zero number multiplied non-zero determinant, so the whole product determinant Y non-zero. So Wronskian non-zero, that means these M vectors and Y vectors must be linearly independent. Okay, yeah. So we, use the linear algebra basic knowledge to help us get everything, all the concepts connected for this part. Yeah. All right. So then, after we have all the preparations above, we have our conclusion. The conclusion is the general solution for the homogeneous linear system, yeah, ODE. Yeah. All right. So the general solution can be written as the linear combination in this way. Okay? Yeah, linear combination. Yeah. Yeah. Here. How do we understand this expression? Yeah. Here. Let me elaborate. How to understand. When you view the formula here, Y formula here. Yeah. Yeah. So I like you to pay attention to each term, the structure of each term. Yeah. First, C1, C2, Cn, all scalars. Yeah. Scalars, single numbers. Okay, scalar. All E functions also scalar. Yeah. Single number. Yeah. All right. Then the capital, yeah, the capital letter based on our convention, vectors. N-dimensional vectors. Yeah. All right. So first, you can treat Y is a linear combination of n eigenvectors, right? Yeah. N eigenvectors. The coefficient is C1 times E function. C coefficient times the corresponding E eigenvalue, T, as the coefficient. Yeah. These two numbers together as the coefficient of each eigenvector. So that's one way to look at linear combination way. Yeah. One view. There is a second view. Second view. All right. Second view is like this. The same expression. Yeah. Here, this time, we look at the variable part. So what is the variable part? Variable. Variable is t, right? T is a variable. Okay? Yeah. Yeah. Other than the t part, everything else is constant. C1, C2, all these little c, all constant. Yeah. Other than c constant, all eigenvectors, they are also constant vectors. Yeah. Eigenvectors, that means there is no t involved in these eigenvectors. No t. Yeah. Inside x, no t. Yeah. So we treat all x vectors as constant vectors. Yeah. All right, so with this understanding, then this time we want to put the C1, X1 together. Okay? You treat this whole thing together. C and Xn, whole thing together. We treat, that's a vector. That's a vector. Okay? C1, X1 vector. That vector, we can treat it as a vector coefficient of this function, E function. Yeah. But this time, the coefficient could be vectors. Vectors are allowed to be used as coefficient. Okay? Yeah. Because we just write it component-wise, right? Vector, we have many components. Yeah. So when we write explicitly, each component, it's a coefficient, right? But now we put them together, C1, X sup 1, we treat this constant vector. This is a constant vector, no t involved. Okay? This constant vector here, it is used as a coefficient of this variable E function. That's our second view. Yeah, here, I point out two different views. Yeah. Because many times, the views are different. The views are important. Yeah. The views give you a good understanding angles, different angles to understand the same thing. Yeah. Yeah. All right. And this one can be represented in a simple form. Y matrix times C vector, constant C vector. Yeah. Yeah. So here, if you are familiar with, yeah, here, just try to get yourself familiar with the multiplication. Yeah. Yeah. Matrix multiplication. Matrix vector multiplication. So get yourself. Yeah. So we apply the multiplication formula frequently. Yeah. Here. Get yourself familiar with the matrix multiplication. Yeah. With vector, with matrix. Yeah. Yeah. All right. So here, this simple multiplication, capital Y, capital C. So simple. Yeah. All right. Get used to it. Yeah. All right. Yeah. The C, capital C. Yeah. this capital C. Yeah. Here we, in order to save space, yeah, but actually this C is a column vector. Here, if you see, the C should be a column vector here, right? But when we write the C, because the column vector would use a lot of space, if we write it not convenient. So we write it a row vector, then this top right corner we use the capital T, we mean transpose, matrix transpose. Okay? Matrix transpose, yeah. So how do you do transpose? Okay? So you make the row vector to column vector. So that's the transpose. Okay? Transpose. Yeah. Transpose, row column switch. Row column switch. Yeah. Transpose. For every matrix, we can do matrix transpose. This matrix, X matrix, we can do matrix transpose. Okay? Yeah. So get used to the matrix transpose. Yeah. Yeah. Matrix transpose, basically, you swap AJK, you swap these two, yeah, with AKJ. Okay? Yeah. These two entries, you do the swap. Okay? So diagonal entries, the same. Diagonal entries, no change, because you swap each one with itself, so no change. Diagonal, JJ, because the subscript JJ, row number, column number, the same. So JJ with JJ, so no change. Yeah. But the entries away from the diagonal, main diagonal, yeah, JK different. Yeah, JK different, so then you swap. Row number, column number, you swap. So then that's the transpose. Okay? Yeah, here. Yeah. Yeah. Here we apply the matrix transpose operation. Yeah. All right, so that's this slide. Yeah. So we spent a lot of time to get ourselves, two students waiting in the waiting room. All right. Yeah. Next, C.2, method of undetermined coefficients. We learned this method before for order 2 case. Yeah. Here, we just, redo it. This time we switch from order 2 version to order n version. Yeah. We can treat it as a straightforward extension. Yeah. All right, so the first one, yeah. Let's look at example. Yeah. Yeah. Part of 1, yeah, we need to do, with several slides. Find a general solutions of non-homogeneous version this time. Okay? Yeah, so we have A matrix and a G vector. Yeah. So we want to solve this one. Yeah. And based on our knowledge we learned for order 2 equation, this non-homogeneous equation, we split 2 parts. The first part, we find the general solution for the homogeneous part. Second, in order to factor in the G part, the non-homogeneous part, we only need to find a particular solution. Yeah. All right, so here, let's solve it in that way. For the homogeneous part, we start with this eigenvalue problem. Okay? Yeah. Find the eigenvalues of A. We calculate the determinant. Very simple. Yeah. So after factorization, we get 2 eigenvalues. -2, -4. So we have two E functions we can use in our general solution expression. Yeah, so we leave there. Then find the eigenvectors of A corresponding to these two eigenvalues. Yeah. So we need to solve two homogeneous linear system to find these two eigenvectors. The first homogeneous linear system. All right. How to make this matrix? Yeah. So this matrix, we use λ1 as the eigenvector. So let me write it explicitly a little more. Yeah. Because last time, one student asked me, how do you get this matrix? Yeah. So I repeat. Yeah. Last time. Yeah. All right. So here, how do you get this matrix? Right? Yeah. Yeah. This matrix basically, that is the capital A minus λ1 times identity matrix. Yeah. λ1. Okay. All right. Capital A matrix, that is right here, this corner. Yeah. 1, 1, minus 3. Okay. Then lambda minus 2 times identity. We know identity matrix. 1 at the diagonal, so but you multiply minus 2, so you put a minus 2 at the identity. Yeah. Yeah. So you do subtraction on these two matrices at that corner. Okay? So you do that. You do that, then after simplification, you get this matrix. Okay? Yeah. So subtraction, you get this matrix. Okay? All right. Yeah. Now, our next step, we need to find simple x1, x2 value that satisfy this equation. Yeah. The solution not unique. There are many solutions. Yeah. We just want to find relatively simple solutions. Yeah. Okay. All right. So here, remember the last time, because when you use eigenvalue here, the determinant must be 0. If determinant is 0, that means these two vectors are linearly dependent, right? The two row vectors linearly dependent. If linearly dependent, then the second row vector, it's a constant multiple of the first row vector. Constant multiple first. All right. So that means if you have the first equation, then the second equation is redundant. If you have first equation, the row vector multiply this column vector equals 0, because the second one, do the multiplication just a linear, just a constant multiple of the product of the first row and the vector. Yeah. Constant multiple of 0, also 0. Okay? So that means the second equation basically redundant. It does not provide new information here. Okay? If it does not provide new information, yeah, you can just cross out. Okay? So when you solve, you only need to solve the first equation. Yeah. Second equation is satisfied automatically. Yeah. How to find the solution of the first one? Yeah. So last time Max asked me. Here, what I say, yeah, because the number is simple, yeah, -1, +1, these two, you just try 1, 1 here. 1, 1, so 1 times -1, 1 times +1, adding together, you get 0. Yeah. Yeah. Two numbers, yeah, multiply, yeah. So then, for the general case, yeah. So last time at the end, another student here. Yeah. All right. Yeah. So for the general, yeah, because the general case, you may have AB vector, you multiply x1, x2 equals 0, right? You may have a situation, yeah, because here minus 1, positive 1, very simple. But for the general AB, when you do it, so you may feel hard, right? Yeah. So here actually not hard. Yeah. Why? Because AB, how about we just use B negative A? This vector, so AB, we swap AB, we get a BA, but we need make one of A or B negative. Yeah. When you do that, you do multiplication, A times B minus B times A equals 0. Always true, right? Yeah. So for that situation, AB vector x1, x2, if you want to find the solution, you just take B negative A. B negative A, if it's not simple enough, you can cancel some common factors, right? Yeah. If they have common factors, you cancel out. Make it simple. Okay? Yeah, for example, B100, A200. Yeah. You can cancel 100. So 1 and 2. Yeah. So make it look simple as possible. Yeah. So that's the general way to solve this type of question. Yeah. All right. Second one, same. Yeah. So we get a solution. Yeah. Second one, same situation. Two row vectors, linearly dependent. Basically, they are the same. So now you have no problem to see the redundancy, right? The second one, just repeat the first one. It's redundant. Yeah. Yeah. So you only need to find x1, x2, yeah, satisfy the first equation. Yeah. These two numbers adding together equals 0. Yeah. Find a simple two numbers adding together 0, 1 minus 1. 1 minus 1, adding together is 0. Okay? So you get two eigenvectors. Two eigenvectors. Yeah. All right. Homogeneous solution. YH equals C1, first eigenvector, e to the negative 2t, corresponding to first eigenvalue, plus C2, second eigenvector, e to the second eigenvalue times t. General solution. Okay? Our standard form of general solution. So we finished the first half. Okay? To solve the non-homogeneous, now we finish the first half. Next, we need to get the particular solution, YP part. Yeah. All right. How to choose the form of YP here? Yeah. So last time we did one. Yeah. So if you still remember a little bit what we did last time. Last time, remember when we solved that electric circuit question, JP, remember? Yeah. Current I, we do not want to use I matrix because it's identity. So we use a J matrix, JP. Yeah. So here, similar to our JP situation. Yeah. All right. Observation. We need to make a key observation here. So what's that? All right. All right. So here, yeah. Remember. Here, I need to review a little bit. Review our second order linear ODE solution a little bit. Yeah. So because this method we learned in the second order linear ODE. Yeah. We learned it. Yeah. So we need to recall what we did in second order linear ODE. So we did in this way. So when we, right, yeah, so here, because, so this G, yeah, so you have this E function here. Yeah. But E function, if you look at the E function, and the E function related to the eigenvalues, this one happens to be the same as one of the two eigenvalue related functions. Happen to be the same. If different, then it's easy. If different, then we just use a constant vector times this function, directly. That's simple. But if it happens to be, you know, one of the functions in the general solution, then, yeah. Remember, we have three rules. Three rules. We need to bring those three rules. First one, basic rules. Second one, modification rules. The third one, sum rules. Here we need to use the modification rules. Okay? When this function happens to be one of the, you know, functions used in the general solution, we need to use the modification rule. Okay? Yeah. So the modification rules tells us, all right, this function is repeated here. It is repeated here, but only repeated once. Yeah, because it look at the multiplicity. How many times you repeat it? All right, that would determine the structure of your YP vector. YP. When you write YP, you need to give it a structure, right? What's the right structure of YP? Here, we want to figure out what is the YP structure. So we look at this E function repeated. How many times here? Here, repeated only one time. Okay, one time. What do you mean two times? If this -2 is a double solution. Double solution, we treat repeated twice. Okay, so the double solution, if you see, you know, lambda minus 2 square equals 0. Sorry, plus 2. Yeah, plus 2. Then we say that minus 2 repeated twice. Double solution. But here we don't have that square. So it's a single solution. Single solution, so this function repeated only once here. Once here, by the modification rule, we write the structure in this way, apply the modification rule, yeah, based on the multiplicity. Yeah, how many times? The multiplicity is 1 here. Okay, multiplicity 1. Yeah. Here, let me write it out. Yeah. So that multiplication rule, yeah, we will use. So this time, I explain how to use, but later there are several times I need to explain how to use this multiplication rule. Okay, so here, multiplicity equals 1. Okay, so we use the multiplicity equals 1 information to help us. Yeah, so here I just copy the multiplication rule. Yeah, let me read it. If a term in your choice for YP, a term, so here we talk about this, happens to be a solution of the homogeneous ODE corresponding to 4. Yeah, 4, you know, the original equation. Happen to be repeat. Yes, here, repeat. Okay, multiply this term by x. Yeah. Here, multiplicity is 1. You multiply by x. Okay, or by x squared if the solution corresponds to a double root. Yeah. If you have a double root, you need to multiply x squared. Okay? And so on. All right? Yeah. Of the characteristic homogeneous. So that's the modification rule. Okay? Yeah. All right. All right. So here, yp, based on this one, all right. U vector, v vector, two vectors to be determined. Look at the title. Method of undetermined coefficients. What are undetermined coefficients? Here, these u, v, these two vectors, we treat them as undetermined coefficients. Vector coefficients. So this place, vector coefficients. Okay? Vector coefficients for these two functions. Okay? These two functions. Yeah? All right. Yeah. Okay? So u, v, to be determined. All right. We will calculate capital U, capital V. Sorry, U and V.
Okay.
Question.
Just a quick question with if it was the multiplicity was 2, and you multiply one of the terms by x squared, would you multiply the first term by x, or would it just be n?
Right. Yeah. Good question. Yeah. Actually, I think. Yeah. So yeah. So if yeah. Let me explain. Yeah. Actually, that's a very good question. Yeah. Here, let's consider if multiplicity equals 2. Okay? All right. The best structure we write in this way. Okay? All right. So we write this equals U1 T e to the plus U2, yeah. U1, we still keep that T, all right? Yeah. U2 T squared plus V. Okay? Yeah. So U1, U2, okay? For the general case, yeah. All right? Yeah. Because it covers more possibilities. Okay? Yeah? Yeah. Some of the people they may skip this U1 term. Okay? Only use U2. That's a special case U1 equals 0, right? So if you skip U1, that's a special case you make U1 0 vector. Then its term is gone. But there is a possibility if you skip U1 term, if you try this structure, you may not be able to find a solution. Yeah. Yeah. If you're lucky, you can find a solution. But if you're not lucky, you cannot find a solution. Yeah. So that's why if we add another term, U1 term, then we have better chance to find a solution for double roots. Okay? Triple roots, you add another term. Okay? U1, U2, U3. How about that? Yeah. It's more complicated, but the idea is like this. Okay? It's very complicated, but the idea is like this. Okay? Yeah. You can use computer to help you. Yeah. But the idea, the concept is like this. That's the way we apply this modification rule. Okay? Yeah. All right. Go.
Are we only working with e to the negative 2t right now, or what happened to e to the negative 4t?
Don't worry, because it does, yeah, it does not, it's different. It's different, so we don't worry about it. Yeah. Yeah. Think about this. Yeah. All right. Yeah. Good question. Yeah. Because it helps us understand this whole solution better. Yeah. Let me change this -2 to -3. How about that? -2 to -3. Yeah. Because if I make this change, then it does not appear anywhere in YH, right? Yeah. So if we change to e to the -3t, if we make this change, -3, it does not appear anywhere here. then the whole thing gone. Because you can see, so why, when it appears somewhere, we need to get that function involved. If it does not appear, then the structure completely different. Yeah. Because we only want to match the structure. If we need to choose something here, because there is overlap with the structure, right? There is overlap. So we should take care of the overlap part. If it's different, it does not appear, there is no overlap. Or we say overlap part is 0. So we do not need to assume anything from the YH part. You just, all right, for that negative 3t, our structure, we just write this. Y3t case, structure, you just write yp equals v. Let's just use one vector, v. V times e to the negative 3t. How about that? Yeah. No term from e to the negative 2t, no term from e to the negative 4t. Yeah, because, no relationship. Yeah. Yeah. So that's the way we apply, this undetermined coefficient, this method. Yeah. Yeah, a little messy, yeah, but hope you can see it clearly. Yeah. Yeah. All right. Now, let's take derivative yp in two different ways. First way, second way. First way, we take a derivative directly, but we need to apply chain rule here. Sorry, not chain rule, product rule. T times e function, we apply product rule, okay? So derivative on t, that's 1 times this e function, u times e function, yeah. And derivative on the e function, so the second term. Yeah. Then derivative on the v term. That's the first way, okay? Second way, we go back to the original equation to get the yp. Yp prime, A matrix times yp plus g. So the second way, okay? So A multiply this vector plus the g vector. These two expressions should be the same. Same vector, you use two different ways to represent, so they should be the same. All right. Yeah, so yeah, hope, yeah. So if you want to copy something, yeah. All right. Yeah. All right, yeah. Hope you can see it clearly. Yeah. Derivative. Yeah. All right. Yeah, so a little complicated. Yeah. So be patient. Yeah. So when we solve these equations, be patient. Yeah.
The v term is gone in that last one.
V term. Yeah. All right. A times this whole vector. Yeah. A times the first term, A matrix times the second term. Then this is G part. Yeah. So V is still here. Okay? Yeah. It's still there. Yeah. This is a G. Yeah. All right. So the next slide, we want to find U vector and a V vector. Then we solve the problem. U vector, V vector. Okay? Undetermined coefficients. Yeah. All right. Continuation. Yeah. All right, so the first expression, second expression, they should be the same. They should be the same. Yeah. How to establish some equalities from this equation. Yeah. So we need to look at the All right, so here, let me recall the view. Remember, I talked about a view we used before using vectors as coefficient. Yeah. Here, I like you to, when you look at the formula, it's a long formula, but treat u vector as a coefficient of this e function. Okay? Vector as a coefficient. Yeah. Because it's a constant vector. Constant vector, so we treat it as a coefficient. 2u here, negative 2u, coefficient for the second term, and so on. Okay? Coefficient. All right. If you treat it in that way, so then you look at the function part. E to the negative 2t, e to the negative 2t, here t times e to the negative 2t. Yeah. This function is different from those two. Yeah. These two functions the same. We can combine these two terms, right? Yeah. We can combine the terms. All right. Here, these two functions the same. We can combine the two terms. So t times, so this term and that term, they have the same function part. Okay, same function part. All right. So the first one, after we combine the terms, we get this expression. Yeah, u minus 2v, the new coefficient. Okay. Okay. Yeah. Here, we combine the term, we get this expression. Okay. They should be the same, so the t times e function, t times e, this term should be the same, and e to the negative 2t term also should be the same. Yeah. So we compare the corresponding terms and get new equations. Yeah. So the new equation, yeah. So if you, here we compare this t times e function, this term, we get au equals negative 2u. Okay? When we compare this function, tu. Okay? Yeah. So the first equation, we compare this term and that term. Yeah. That term. Yeah. Okay? Yeah. 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 Same function part. So their coefficient part should be the same. Yeah. Second, yeah. All right. Now here, if you look at this equation, you can see u is an eigenvector of A matrix for eigenvalue negative 2, right? Look at the form. That's our eigenvalue problem, that form. Okay? With eigenvalue negative 2. Then we can find u. U is an eigenvector. Yeah? So A minus lambda identity 2. Look at this matrix. So the U is just this matrix, 1, 1 matrix. Eigenvector. Yeah. Eigenvector under negative 2 eigenvalue. Yeah, we did before. Yeah. Here we repeat it. I just copied what we did before here. So this is the U vector. Okay? U vector, but for U, you want to associate a constant A with it. Yeah. Because remember, our title we call undetermined coefficient. U is undetermined, so we should attach that undetermined A with it. Okay? Yeah. We know it should have the vector structure, that vector direction. It should follow, but how to follow that direction? You use A to control the scale of U. Yeah? U could be larger, could be small. So use that A to control that. How large is that U? Okay? Yeah. So we make U equals A times the first eigenvector. All right. So after we have U, then we look at the second equation, but this time we compare the corresponding terms. This time E2 function and the E2 function here, but we only compare their coefficient. Their coefficient, both sides, should be the same, so we have this equation. Second equation. Okay? Yeah. All right. Second equation, after simplification, we can write in, V part, U part. U is this one. Okay? U is A plus 6, A minus 2. Yeah. V part. All right. How to find V and A here to solve the whole problem? How V, A, solve the whole problem? Yeah. All right. Yeah. So here, V, let's use V1, V2. V, we use V1, V2. Okay. Find V1, V2. We need to solve this equation. Okay. All right. Then, do the matrix vector multiplication. V2 minus V1, V1 minus V2 equals this vector, right-hand side. A vector with A variable there. All right. But left-hand side, you can see these two entries adding together should be 0, right? Yeah. These two entries, you see adding together should be 0. That means these two entries adding together should also be 0, right? Yeah. The right-hand side, A plus 6 and A minus 2 adding together should be 0. Okay? There, you get an equation, A plus 6 plus A minus 2 equals 0. So you find A equals minus 2. Yeah? Otherwise, you cannot solve this equation. Okay? You have to, only when you choose A equals -2, you can find a solution of this one. Otherwise, no solution. If A not equal to -2, there is no solution. Okay? So we have to choose A equals -2 here. Yeah. All right. Now let's go back. When A equals -2, so U vector is determined. Okay? Undetermined coefficient. So now we determine the U vector. First coefficient, U vector coefficient. Okay? All right. V vector coefficient, let's continue. V vector, V2 minus V1, you plug in A -2, it should be 4. So V2 minus V1 equals 4. Can you find a simple V1, V2? Yep. Two variable. How about V1 equals 0? You choose V1, 0. Yeah? You have freedom to choose. Okay? So choose V1 equals 0, V2 equals 4. So you get a V vector determined. Okay? Yeah. All right. So U vector, V vector, you can write, so here I just write a final solution. Yeah. Final solution here, I just, YP, we can write a YP out. YH, we combine YP, YH, this is the final solution. Okay? Yeah. All right. Yeah. Break time.